right? Okay. So I want to welcome you to another exciting statistical topic. Of course, today the focus is going to be on jointly distributed random variables. Of course, the other time I actually started with what we call random variable. Of course, I introduce you to how we can actually use probability distribution to represent a particular random variable, whether discrete or continuous. When we're talking about discrete random variable, of course, the probability associated uh, with that is basically, we call that probability mass function, okay? And we are talking about for continuous, for continuous random variable, the probability distribution is called the probability density function. What we did the other time, we only focus on one variable at a time. When we focus on one variable at a time, so that is basically univariate. But what if in a situations where we basically want to we actually want to characterize relationship between two variables, and then these variables are jointly represented by a particular probability function. Give me 1 second. I don't know why this is actually okay. I think it's kind of stable now. Okay, so jointly distributed random variable is what we actually what we want to focus on today. I'm sorry about the ways. Maybe later I'm actually going to reach out to the tech on that. Okay, so in the outline, of course, the same way when we are dealing with a single random variable that is discrete, of course, we use probability mass function. But what if in a situation where we have more than one variable that is discrete? Okay, of course, then we're basically going to have a joint probability mass function. So I'm actually going to walk you through that today. Now I'm also going to walk you through a situation where we got more than one variable and each of these variables is continuous. Okay, can we have a probabilistic representation of variables, that are continuous? Then that is going to be called joint probability density function. Then I'm also going to walk you through application. The application that I'm going to walk you through today is basically going to come from politics. Some could come from medicine and so on like that. So let's get started. Okay, so you have can you just give me 1 second and let me see what is happening here? Just want to see why it's now stable. Okay, let's see. Okay, so if I have x and y, x is a random variable, y is a random variable, and the two of them are discrete. Okay, and the probability representation of these two variables that are discrete, we're basically going to call that joint probability mass function. So, which means P of S comma Y, maybe I want to find what is the probability of an uppercase S equal to a particular realized value, and Y equal to a particular realized value. I'm talking about PA now. I'm talking about more than one variable, but each variable represents different stuff, but they are both discrete. It doesn't matter. They may have a different state space. The state space of X may be different from the state space of Y. You remember in the last class, I actually walk you through the state space. We thought the random variable was actually a repair cost. So what if in a situation where I'm talking about repair cost and something else, and each of them is discrete? I basically want to have a way to capture the two variables at a time. Because the two of them are discrete, and I'm basically going to use the idea of a joint probability mass function. Now, in that situation, since I'm having two variables, I'm not going to be using a single sum. I'm going to be using double sum. For two variables, we're basically going to see double sum. For three variables, we're going to have triple sum. The number of summation sign you're basically going to have depend on the numbers of variables. Does that make sense? Okay, so that's what you see now. Okay, do you know from the given joint distribution, we can basically figure out the probability of the marginal. I'm focusing on X and Y. The X and Y are actually represented by a particular probability function that I call joint probability mass function. And I'm not interested in all these two variables. I only want to focus on X, but I have X and Y. So what am I going to do if I want to get X, if I want to get a function? So which means what I want to explain now is more or less like I got a joint PMF and I want to figure out the separate probability mass function for each of the variables. If I'm interested in X, if I'm interested in a function of X, all what I'm just going to do is to sum the joint over the variable I'm not interested in. P of X, I'm interested in the function of X, but I'm going to sum up the joint XY with respect to Y because I'm not interested in Y. If I'm interested in Y, take a look at the other hand. If I'm interested in Y, then I'm actually going to sum the joint with the respect, over the range of the variable I'm not interested in. Does that make sense to everyone now? How to figure out the marginal probability function? In a situation where we are working with a joint probability mass function. Now, I'm going to give you an example now. But before I go into this, I would like to tell, I would like to first tell you what are the examples of discrete and continuous random variable. Okay, I'm talking about the height and weight of a person. I'm talking about the temperature and the rainfall of a day. Okay, now these are combination of examples of discrete and continuous. But specifically, if I want to focus on discrete now, okay, and I have two variable situation. One variable is discrete, the other variable is also discrete, but they are not the same. Take a look at this example. We are interested in the effect of seatbelt use on saving lives. If we consider the following random variable x1 and x2 defined as follows. The x1 is 0 if a child survived. The x1 equal to 1 if a child, did not survive. Because of that, I'm actually going to say x1 is just talking about the nature of survivor, whether somebody survived or not. That is discrete. The state space here is 0 to 1. So that a child survived or not. Now let's now go into another variable, S2. Another variable, S2 is basically going to be talking about whether S2 equal to 0 if you don't use any bets. Okay, and S2 equal to 1 if adult bet is used. S2 equal to 2 if a child's seed bet is used. Oh my God, we got two variables now, but the two variables have different state space. The first variable has two levels, which is either somebody survive or not. That's two levels. But the second variable has three levels, 0, 1, 2. Of course, whether the x2 equal to 0 when no seed bed is used, and s2 equal to 1 if adult bed is used, and s2 equal to 2 if a child or seed bed is used. So which means I got x1 and x2. even though they are discrete, but they don't have the same state space. X1 is 0 and 1. The state space of X1 is 0, 1, but the state space of X2 is 0, 1, 2. Any question on this? Any question? So far, so good, right? Okay, now this is an example. But you know what? Based on this, we're basically going to have a contingency table, a cross tabulation table, because two variables are involved. We're basically going to have, take a look at this now. The table that you are seeing now actually represents the joint probability distribution of X1 and X2. Okay, the joint probability distribution of X1 and X2. What is the essence of this table? This is a multiplication table. This will give you the different possibilities of the joint of the, the levels of X1 and the level of X2. They're basically going to interact. Now 2 by 3, that will give you 6. Then we're basically going to have 6 possible numbers for the multiplication. Now let's take a look at our X1 for 0, 1, X2 for 0, 1, 2. What is the meaning of 0.38? Oh, the meaning of 0.38, that is the probability of X1 equal to 0 and X2 equal to 0. What does that mean? Oh, X1 equal to 0, the probability that the child survived, given that the probability that the child survived and no seedbed was used. That is what it means. Any question about other values in the table? I mean, it's 0 from 0.38, 0.17, 0.14, 0.02, 0.24, 0.05. Those actually represent the different combinations of the levels of the two variables. But let me tell you this. What if I'm interested in calculating the marginal? And if I'm interested in marginal, maybe I basically want to find, let me first write this one here before, maybe basically I want to find the probability of X1. What if I want to find the probability of X1 equal to 0? Or I want to find the probability of X1 equal to 1. Okay? I want to find the probability of X1 equal to 0, and I want to find the probability of, now if I'm doing that, I'm basically focusing on marginal. So I'm going to be focusing on marginal. So if, like I said, if I actually want to, have the probability, if I want to find the probability of X1 equal to 0, then the probability of X1 equal to 0, then it means I'm actually going to sum X2 over X2 from 0 to 2, okay, of the f of x, y. Does that make sense? And that means I'm actually going to add 0.38 to 0.14 to 0.24. That will give me 0.76. Therefore, this guy now, this is 0.76. Okay, then what is the probability of X1 equal to 1? So I'm actually going to do the same. Okay, but let me tell you, when I'm doing the same now, okay, I'm still going to sum, only that I'm summing 0.17, 0.02 to 0.05, and that will give 0.24. Of course, this guy and this guy must add it up to 1, because we only, in the state space, X1 is, that is the state space for X1. Now, I may also want to do the same, okay, for the probability of S2 equal to 0, probability of S2 equal to 1, probability of S2 equal to 2. So when I'm doing that, I'm summing over the range of X1. Any question on what you've seen on the board? Any question now? This is what you've seen on the board. Any question? They are super easy, right? Okay, then I'm going to go to the next slide. Now, what if in a situation whereby I want to find the probability that a child will both survive and be in a child seat? Of course, that would be x1 equal to 0 and s2 equal to 2. If you want to find that, you just need to go to the multiplication table where you have that. Look at that. There's 0.24, right? So that's a joint. Okay. What if I want to find the probability of S2 equal to 2? Okay. Of course, the probability of S2 equal to 2. Okay. I'm actually going to sum S2 equal to 2. I'm actually going to sum over the range of X1, which means I'm going to add 0.24 to 0.05, and that will give me 0.29. Any question? Any question on this? Okay, now I quickly want to go. Now we focus now on the discrete situation where we have more than one variable. Now let's go into the situation where the two variables are basically going to be continuous and not discrete. Now in that situation, the name of the probability distribution now will be called joint probability density function, joint PDF. And of course, the probability of x and y, x comma y, lies in a particular, parameter space. I'm basically, instead of having two summation, I'm actually going to have two integrals instead of two summations. That's why you see integral, but let me tell you, just like the same, just like the way we have different, that we may have a different state space for x and y in the discrete, we can also have a different state space for x and y in the continuous. Now the first integral, I'm basically going to use the range of x, the second integral, the range of y. The antiderivative I'm actually going to do is going to be a sequential one. If you look at what I'm displaying on the board, okay, where I have f of x, ds dy, double integral. Of course, ds dy means I'm actually going to first integrate with respect to x. I'm actually going to integrate the joint PDF, okay, with respect to y force, and I'm also going to do that with respect to x. Of course, I'm going to use the range of x. I'm also going to use the range of y. So that is exactly what I mean. Okay, so from there I can actually figure out the marginal probability density of function. For instance, I got x, a joint PDF of x and y, and I'm not interested in the two. I'm only interested in maybe I'm interested in S, or I'm interested in that the PDF of Y. So if I'm focusing on the PDF of S, so it means I'm actually marginalizing. So which means I'm going to integrate the joint with respect to Y. So which means I'm integrating with respect to the variable I'm not interested in. And of course, if I'm doing that, I'm actually going to use the range. Okay, so what I'm actually going to use as the state space is basically going to be the range of the variable I'm not interested in. The same thing also applicable to when I'm looking for f of y. I'm basically going to integrate f of s with respect to x, because I'm not interested in s. The range of the integration is basically going to be the range of x. Okay, so if that is taken now, I want to move to an application. Okay, I've just introduce you to joint probability distribution situation where S is continuous and Y is continuous. I want us to use this bank example now. Okay, if we let S represent the proportion of time the driving facility is used in a particular bank, and if Y represent the proportion of time the work off by a facility is being used, of course, we've been able to have a joint probability density function looking at the situation, you know, over time. Of course, the mathematician have already, developed, this model, so which happens to be the joint probability density function for X and Y. Of course, the range of X is actually between 0 and 1. The range of Y will be between 0 and 1. Of course, that is the typical range for proportion. Okay. Now, before a meaningful inference can actually be done on this, because on this particular joint probability density function now, the interest may be on maybe I want to get f of X, or I want to get f of Y, or I may want to get what is the conditional function of X given Y, or conditional function of Y given X, because in a particular bank, they may want to see whether a relationship exists between the proportion of time the driving facility is used and the proportion of time the work-off facility is used. And another thing is they may also want to figure out, okay, if they have a certain value for the proportion of time the work-off facility is used, they may want to figure out, what is the probability that the proportion of time the driving facility is used is this, given that the proportion of time or the work-off facility is that. So, moving forward, if we want to answer any question that has to do with statistical, making inference, we need to first investigate whether this guy here, okay, is a valid PDF. And the only way to tell, is if I actually, over the range of X and Y given, when I, conduct the double integral, basically want to see whether this guy is going to integrate to one, because just like what I showed you the other time, when I was working with the univariate, okay, where I showed that the integral f of S ds over the range of S equal to 1, we basically also going to do the same, okay, for for the joint density function. Okay, so what I'm basically going to do now, I'm actually going to make use of my whiteboard, okay, for me to be able to do that. Give me 1 second. Okay, so sharing my whiteboard now. Okay, so the f of x, the joint f of xy, okay, is actually 6/5. Okay, it's actually 6/5 x plus y squared. Okay, and of course x actually lies between 0 and 1, okay, and y, okay, also lies between 0 and 1. And of course I said the x actually x and y represent proportion, okay. In a bank they have a working facility, and they also have a drive-in facility. Okay, so what I want to investigate now is to see whether this guy is basically going to integrate to 1. Okay, so I may decide to start with integrating that with respect to x, and after that I'm actually going to do that with respect to y. So which means I want to show that, of course, the range, of X is from 0 to 1, and the range of Y is also from 0 to 1. So if I want to do that now, so which means I'm actually going to plug in this guy, okay, here. So integral of 0 to 1, then it's 0 to 1. So instead of f of s, so I'm basically going to have 6 over 5, okay, into x, okay, plus y squared, okay, so the x, okay, the y, okay. I basically want to see whether the total area under a curve is going to be 1. Okay, that we need to verify that before we can actually conclude that that is a valid PDF. And of course, for it to be a valid joint PDF, that is highly required. It validity, that validity is required, before one can conduct what I call any meaningful inference. Okay, so 6 over 5 is actually constant. I can actually bring it out. So I can write 6 out of 5, right? So that is how, right? Then integral of 0 to 1. And right now, so I for first want to focus on you know the x aspect. So when I integrate that with respect to x, I'm actually gonna have s squared divided by 2, and this guy is a constant now because I'm integrating with respect to x. So I'm actually gonna have x y, okay, squared. Okay, when I have that, I'm actually going to plug in 0 to 1. Okay, so when I plug in 1, so let me first write 6 over 5. Then when I write 6 over 5, okay, I'm actually going to plug in 1 to wherever I see s. So that's going to be 1 squared, okay, over 2, okay, plus, then I'm actually going to have 1, okay, then y squared. Okay, so when I have that, when I decide to plug in 0 to where I have s, and I subtract, of course, the other one is basically going to be 0. And of course, don't forget, I still have integral sign, 0 to 1. Okay, the y, okay, don't forget. So the y here. Okay, so what I actually have now, so if I simplify, so I'm actually going to have 6 over 5 from integral from 0 to 1. Okay, so I'm actually going to have 1 over 2 plus y squared. Okay, now it is time now to integrate this guy, okay, with respect to y. Of course, I'm actually going to have 6 out of 5, okay, integrating this guy now. So that's going to give me half y, okay, you can put a bracket, okay, plus y raised to power 3, okay, divided by 3. Okay, so when I do that, I'm actually gonna plug in 0 to 1. Okay, so I'm actually gonna have 6 over 5. Okay, so when you plug in 1, that's gonna be 1 over 2, okay, plus 1 over 3. Okay, of course, when you plug in 0, by the time you subtract that from 0, you basically gonna have just this guy, and of course this is gonna give me 6 over 5. And of course when you try to simplify that, so that should give you 5 out of 6. Okay, and you know what, this guy cancel this guy cancel that guy. What do I have now? Then I got 1. Then it means I've already validated the join of PDF. Okay, so that is how we do that. Okay, I'm actually going to stop my share now, and I'm going to go back to the material. Okay, so I'll give me 1 second. Okay, so this is material now. Okay, so I think I've been able to show that now. Okay, I've been able to show that. Okay, so another thing that we want to do, what of in a situation where we want to show that X and Y are independent. You know, I told you the other time in this bank, the administrator in the bank may want to see whether the proportion of time the driving facility is used is independent of proportion of time the work-up facility is used. Okay, so that they are independent or not. Okay, so what are we going to do? So it means if I'm able to get the f of x, which is a marginal density of x, and I also get the marginal density for y. So when I multiply the marginal density for x and the marginal density for y, and if that automatically gives me the joint probability density function, you know, connecting x and y, then I'm basically going to conclude that my x and y are independent. Okay, so independent actually means, okay, you know, the proportion of time driving facility is used. Okay, it does not really depend on the proportion of time the working facility is used. Okay, that is what we mean. Okay, so we may also want to answer a question that has to do with the conditional density function. Of course, you know, this is the definition, the mathematical definition for that. If I want to get f of y given s, because for me to be able to answer a probability question that has to do with what is the probability of maybe y less or equal to something given that x equal to something, then I basically need the conditional distribution of y given s. Okay, we in the similarly we can also have you know, f of x, okay, given y. Okay, remember the idea of you know, probability that we've done before, conditional probability. So this guy also going to be a joint, okay, is going to be a joint, okay, divided by f of y. Okay, so and that's f of y is basically going to be the marginal density of y. Okay, so I wanted to take note of that. So but the one thing is our f of s must have to be greater than 0. Okay, so there's another question here. Okay, you know, you're giving f of xy equal to that. So, and then they wanted to figure out what is f of x, what is f of y, and what is the f of s given y. Okay, so you follow the way I explained that the other time. So, if you want to get you know, if you want to understand how they figure that out, so you just need to do f of s is basically going to be equal to you know, if you take a look at that now, okay, it means you need to integrate this guy, okay, you need to integrate that guy 1/6, okay, into x plus 4y. Okay, you're actually going to integrate that with respect to y. Okay, and you're basically going to use the range of y, so which is going to be from 0 to 1. So when you do that, you're basically going to have this. Similarly, if you want to get the f of y, okay, so you can practice that. All what you just need to do is to integrate that same joint probability function. Okay, you're going to integrate that same joint probability function with respect to the variable you are not interested in. Okay, of course, if I'm focusing on y, I'm not interested in s. And what is the range of x? Okay, it's from 0 to 2. So when you do that, you're basically going to have this guy here. Okay, so the f of s, the f of y, they're basically the marginal probability. Okay, so now, so you can easily get this guy. It's just going to be the conditional distribution of L or S given Y is just going to be the ratio of the joint probability, which is what you're given initially, divided by the f of y that you just find out. So all what you're just going to do is to find the ratio. And when you find the ratio, you're going to simplify that. So finally, this is what we have. So that actually gave, you know, that is a conditional, you know, S given Y. Okay, so of course, you can now use that to answer a probability question. Take a look at this guy now. Okay, this guy is actually asking you to find the probability of x less or equal to 1, given that y equal to half. So if I want to interpret this guy now, so basically, this is what you want to find. You want to find the probability of x less or equal to 1, given that y equal to 1 over 2. So what you actually want to do here, you need to first derive the f of x given y. Don't forget, this is probability of x less or equal to 1, or given y equal to half. So you need to first derive, you need to first get this. So we've gotten this guy now, right? We've gotten that guy now. So you now need to plug in y equal to half. Okay, so when you plug in y equal, that's exactly what I'm doing here, trying to plug in that. So finally I got this. Okay, when I got this guy now, then I can now figure out the probability of x less or equal to 1. So which means I'm basically need to integrate this guy now. So I'm basically need to do s less or equal to 1. What is the range of x from 0 to 2? So I'm actually less or equal to 1 means I'm going to go from 0 to 1. Then I'm going to integrate x plus 2 divided by 6. Then I'm going to do the x. So when I do that, then I'm going to after integrating that, so I'm actually going to plug in 1 and 0, and I'm going to subtract. So when I do that, so you're going to see the result now. Okay, so finally the result is basically going to be 5 over 12. Okay, so that's exactly what you're going to do. Okay, now another thing that I'm going to show you, give me 1 second. Okay, so going to the next question now. Let me clean up my board. Okay, so the next question now, let x and y denote the proportion of two different chemicals in a sample mixture of chemicals used as an insecticide. Okay, suppose x and y have joint probability density given by, okay, so in this situation now, the joint probability density is actually a constant too. At times we can have a constant function. Okay, so the range of x is from 0 to 1. The range of y is from 0 to 1. But there's another additional information. Adding x and y, have to be less or equal to 1. Don't forget the proportion, what they're trying to tell you. Okay, the proportion of the two chemicals. Okay, x and y that you actually want to use as an insecticide when you have them together. The maximum they can be is 100%. That is less or equal to 1. They can be less than 100%, or they can be exactly 100%. So which is the addition of that. So I need you to look at that. So that's additional information. Okay, so what you're now going to do now is the question now is find the marginal density for x and y, and are x and y independent? Then you are asked to find the probability of s greater than half given y equal to 1 over 4. Now, the very first thing now, if you want to find the marginal means, you basically want to find the marginal density for x is f of x, the marginal density for y is f of y. Okay, don't forget the other time I said, if you basically want to get the f of x, or what you basically going to do is to integrate, okay, the joint f of x y, okay, with respect to the variable you are not interested in. And right now, so don't forget about this additional information given, even though x lie between 0 and 1, y lie between 0 and 1, or what you just also need to put into consideration is just like the addition of the two variable have to be less or equal to 1. And you know what, when I want to make use of this now, so I can basically say, okay, x equal 1 minus y, and at the same time I can also say y equal 1 minus x. So that is the reason why here the range of y here is basically going to be from 0 to 1 minus x. Okay, 2 is the f of x y. Okay, I'm also going to do the same for this, and in the end when I integrate 2 now with respect to y, that's going to give me 2y, right? Then I'm going to plug in 1 minus x, I'm going to plug in 0, I'm going to subtract, finally I'm going to get this for f of x, finally I'm going to get this for f of y.
But the fact still remain that the range of x is from 0 to 1, okay, naturally, and the range of y from 0 to y. If you really want to know whether your result is correct here, okay, all what you just need to do is to see whether f of x is valid PDF. By integrating this guy again, you can integrate this guy and use a range of 0 to 1. Okay, if actually give 1, then you are right. Okay, this is what I mean. If you do the integral 2, let me put the 2 outside, and you do 1 minus x, okay, dx, okay, and you basically use 0 to 1, okay. So this guy is going to be x, right? This guy is going to be s squared, right, over 2. Okay, now you want to use 0 to 1. Okay, don't forget this too, that everything is going to multiply that out. So when you plug in 1, okay, and you plug in 0, so when you plug in 1, so that's going to be 1 minus half. So you're basically going to have 2 multiplied by half minus 0 at the end of the day, and automatically that is going to give you 1. So which is show that that is valid, that your answer is right. So you're going to do the same thing to this as well. Okay, the next thing we will now want to do now is want to investigate is whether x and y are independent, and the only way to investigate that, I really want to show whether the f of x y can be a product of f of x, okay, and f of y. So which means if I multiply this guy by this guy. Of course, when I multiply that guy by that guy, okay, the result here is basically going to be 4, okay, into 1 minus x, okay, and 1 minus y. So, and that is not equal to the f of x y. Don't forget, the f of s y given, okay, the f of s y given is actually 2. So 2 is not, so that is not equal to that. So because of that, you're basically going to say x and y are not independent. Okay, the x and y are not independent means they depends. Okay, they depend. Okay, so that is what it means. Okay, so the next question now is asking you to find what is the probability of s greater than half given y equal to 1 over 4. Of course, before you what you need here, you first need a function, a conditional function, f of x given y, and after that, of course, if you want to get that, of course, it's basically the ratio of s comma y, okay, divided by f of y. Okay, don't forget, your f of xy is actually 2, okay, divided by your f of y is 2 into 1 minus y. Okay, so that cancels that. So in the end, so that's going to be 1 over 1 minus y. Okay, so when you have 1 over 1 minus y, you're going to plug in 1 over 4. Okay, so when I plug in 1 over 4 now, so it's going to be 1 minus 1 over 4. Okay, so that is basically going to be 1 over 1 minus 1 over 4. Let me see. If I have 1 out of 1, 1 over 1 minus 1 over 4 is basically going to be 4. That will be 4 minus 1. That's going to be 3 over 4. Okay, that is looking like 3 over 4. So I'm going to have 1 over 3 over 4, so which is going to be 4 over 3. Okay, so when I have 4 over 3, or what I'm just going to do now is to be able to find what is probability that s greater than half. So you're greater than half, so half. Okay, what is the last range of, so half to 1, okay, 4 over 3, okay, 4 over 3 dx, okay, so which is basically going to be 4 over 3x, okay, then from 1 for 1 over 2 to 1. So when I plug in 1, so basically I'm actually going to have 4 over 3, 1 minus half, right? Okay, so 1 minus half. I think this is going to be half, right? So what I'm thinking now is that I'm actually going to have 4 over 3 times half.
okay, 4/3 times r, right? And 2 goes here to, that is likely going to give me 2/3. Okay, that's going to give me 2/3. Let me see what I got on the other hand. Okay, so that's exactly what I got. So 2/3, take a look at that. Okay, okay, so this is where I'm actually going to stop. Okay, make sure you stay safe and have a lovely weekend. So bye for now, everyone.